Alright, so the memory organization is how the memory works on the pick. So something that you should really pay attention to. I just showing you all what you need to know. It goes deeper, but I can't show you everything in one video because it'll be too much. So I kind of showing you all what you need to understand to start the code, and really and truly, unless you want to go real deep into it, it's really all you need to understand, because once you get it, you'll know where to go for it. So this is page 25 in the pick. So assuming you have this pick, you could go ahead and download it. So the memory organization, basically it's broken down into program memory, which is basically where your actual code is stored. So the lines of code that you have, it's stored in program memory. And then data memory is where you store like constant values that you have. So let me say you want to store 20 to do a delay or something, that will be in your data memory, and it will be specifically in your general purpose RAM. So your special function registers, like the registers we did, like the POR, the LATs, and all those are special and core registers. You'll find those in those two. And the other two, you really had to worry about. So your data memory, it stores your constant values, and your program memory is just where your actual code is stored. So it'll be based on your configuration words and all these other things, which you'll see. So your program memory, so you have this amount of program memory. Whole number, guess, sure. This is it in hex, sure. Remember, program memory is the memory you have to actually store your code. So the more program memory you have is the more complex and larger code that you can actually write to do whatever you have to do, which is a lot. You ain't gonna use all that memory, especially as you're now starting. So, so let me see how best I could explain. So this table here, that kind of shows you some stuff. So how to break this down into more videos, but really and truly what it does do is break down some important stuff. So PC is called the program counter, and it literally says exactly what it does. It just counts. Okay? It counts in terms of your addresses. So it's called the program counter, and it's a 15 bits register. So it actually could go from your first program memory address straight down to the last one. But as I said, it just counts. It literally just counts from 0 straight up to this number here, which is 71FFF your last program memory address. It just counts. And that's useful because you will need to maybe play over that to get to certain addresses. And the other piece of this is called the stack. So basically is last in, first out. Example, that we say you're doing something and your mommy call you. So you go and do what your mommy call you, and you have to come back to doing what you used to do. So what you do, you put it in your brain and leave it there. Go and do whatever you have to do. And when you finish that, you will come back and be like, what I was doing again? And you'll be like, yeah, I was doing this. And you'll just go back to doing it. In a pick language, it stores the previous program memory address, goes to where you want it to go now, and then for you to know where to go back to, it just pops off the last address on your stack, and it just goes back to doing that. So if, example, if while you're doing something, your mommy call you, and if while you're doing what your mommy was doing, your father call you, and if while you're doing what your father calling, your auntie call you, it will just trace back. So when you finish doing what your auntie doing, it will pop back the address, the previous address, which was where your mommy was calling you for, or your dad was calling you for. Then when you finish what your dad was doing, it will pop up the last address that your mommy was calling you for, and you go back to that address. And then when you finish where your mommy was doing, you pop back the last address, which is what you was doing. So it's last in, first out. Like just how this stack does work. And you normally find the stack we kind of use it with like call and return statements, or return from interrupt. Anything with a return, you will need to store the previous address, because the pick will know what to return to unless you give it the program memory address. So that is stack. So the part that you have to remember is this part here. So this is where your program memory is stored. So your first program memory address is something called a reset vector. Cannot start to write code. This is an unknown address. You cannot write memory or write code from that address. These will be 0001 straight to 0003 is unused memory. You don't really use it at all. Then you have your interrupt vector, which is at 004. So what the interrupt vector does is exactly what we are explaining. If while your mommy calling you, that is an interrupt. So you would just jump to that and it just does whatever you want it to do at that moment in time. So we call that interrupt vector. Basically, whatever you want your pick to do, when something external or internal happens, it will be like, okay, what you want me to do? And it will just jump to this address to know what you want it to do. So it's called the interrupt vector address. And then from 0005, you can actually start writing your code. You can actually start it anyway after 0004. You start at 20, 23, anyway you want it to start. But normally people start at 0005. Okay? And then straight down to 7FFF. Because that's your last program memory address. So all in all, you have your program counter. It literally just stores addresses and it just counts incrementally through your program memory. Because that is basically a code. It just goes line by line. Each line, you can think of it as a program memory address, and it just keeps counting, 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 counting. If you wanted to jump somewhere else, what the program counter will do is store that in the stack, then it will jump to the location that you wanted to do now, and it will just pop back the last address to the program counter, and it will go back to where it does. So the program counter stores addresses. That's basically what it is. It stores the current address that you're at, and it just keeps counting for you from 0 straight up to your last program memory address. That is what it does. The stack is used when you have to go somewhere and come back. It just stores the address for you. Your reset vector is here. The interrupt vector is this. And you can start writing your program memory from this address. You don't have to, but once it's after 0004, not before, when it's after, you can get through. So as a program memory is basically stores your code. So we'll go through this in future videos. Alright, so you have your core registers. The register that you need to understand as you're starting off is the working register, which we'll get to in the next video actually. And the last type of memory is your data memory. So as I said, it just stores your variables basically. And there are some other actual memory in the pic that you can't override that you actually need. So that will form your special function registers and your core registers. So your data memory is broken up into 32 memory banks, and in each memory bank you have some core registers, special function registers. You have your RAM, which is basically where your variables will be stored, and you have 16 bytes of common RAM. So one thing you have to remember is when you're doing these things, you have to sell the banks, because in each bank, the pick will know which bank it is. So you have to actually sell the banks to know. But logically, since you're now starting off and you're now starting to code, the first default bank, the RAM there, is more than enough for you to store all the variables. So you will be safe. You just have to know which address to start from, which I will go through. So remember, this is data memory now, not program memory. But you need data memory to do the program in most cases. So we'll go into the status register when we go through the working register, because it kind of linked in a way. Right, so you have your special function journal. So I went through this already. So the part that I want to go through is this big block here. So it's basically the same idea as the program, but it's different stuff. So up to 0C, you have your core registers, which you'll see when you scroll down to the banks. you have a special function registers, and then from 0020 you have straight up to 6FH, you have the area where you could actually store like your little variables. So all in all, if you want to store some variables, the first address that you can store it from, assuming that you start with the first bank, the default one is 0020 or 20. That is where you have to remember. You can start from, so that's different from the program. So program you start from 0005, but this you start from 0020, straight up to 6FH, which is a lot. Here you have to be doing something real complex at this beginner stage to use all that general purpose memory. Alright, so these are your banks. So take a good look at it. So this was the first bank, which is bank 0, which basically we went through just now. So your general purpose memory starting at 20. So if you notice, you have your ports, you have your tris, you have your lats, which is basically the main ports that we went through just now. So you may basically find that in bank 0, which is the default bank. So even if you don't bank cell, it will do the correct thing, but you might get some warnings stating that bank 0 was assumed, so you'll be good. But it's good to bank cell the register that you're going to. So if you're going to port, you bank cell port. So just find wherever bank port in, just for good practice. But the other ones, though, you will need to bank cell it for you to know which bank to go into. If it's not in the default bank, which is bank 0, you have a bank cell as a rule of thumb. And if you notice, each bank have a general purpose memory. It kind of just starts at different addresses. But for now, this is enough general purpose for us to use. And you have 32, so you'll have real banks, so like real memory. Okay, and that is basically memory organization in the most simplest way, just for you to understand. So let's recap. You have your program memory, which stores your code. And from the program memory, what you need to understand is that you have a program counter and a stack. Basically, program counter counts the addresses, it increments the addresses to go through your code. The stack is used so when you had a return or call to go back and forth to know what address it was at and what address to go back to. You have a reset vector and an interrupt vector. So your program memory starts at 0005. Then you could start anything after. So then you have your data memory, which stores the variables and your special function registers and stuff. And the takeaway from all that is if you use any default bank, you have to start at 0020. That's the first address that you can use to store your variables. Okay? And there are 32 banks. Bank 0 is the default. So you'll most likely find your main registers, which you went through in the previous video. If you have a register and any others, you have to bank cell it to acquire it or to use it. If you don't, it will crash. Let me say you wanted to use an digital result low, which is address L, and you didn't bank cell it, it would just assume bank 0 and you wouldn't be able to access it because you're in the wrong bank. And basically, that's it. So if you actually go back to MPLAB now, so you can appreciate why we did what we did. So right now, right there, so what we did, we said organization 0x00. So when our reset happens, what you want it to do, when the program counter increments, it will see go to main, so it will go to main and a reset, which makes sense because if you unplug and plug in, you want it to start at your main routine. So then you might, if you have an interrupt, you might have org 0x04, and when an interrupt happens, you might want to go to interrupt handler, for example. Then after that, you will have org 0x05. So you basically start in your program at this address. So you could actually start this at 20, 89, anything more, or once it's higher than 4. Remember, 4 is the interrupt vector. So you can start at 20 or 21 or 0, 0x05. That's probably the the simplest way to do it. And then after here, you could actually start writing here. So you write main, and after main, you have your end, and your code goes here, which is basically a program memory. Okay, and if you wanted to use your data memory, you normally write it here. So like say how variable, we use EQU when you have a variable and you write whatever you want to write. Whether you wanted to store 20 and so on and so forth. So you could go ahead and store your variable. So you'll be using data memory here. Org program EQU data memory. So I say it will differentiate, or the pick differentiates the two of it. And basically that is the end of your memory organization. So it kind of helped to understand what program memory is and what data memory is and how to use it. Once you understand that, you can go ahead and start to code, which we'll do in the following videos from now. So we'll talk.